Hello everyone. In this video, I want to briefly talk about random number generation in MATLAB. Probably you have used in MATLAB so far commands like rand, rand_n, and rand_i. There should be an n here. We generate random numbers from a uniform distribution, right? From a Gaussian distribution and integer numbers. And if you watch just my previous videos that I use a random generator block in Simulink, you found that if I use something called the seed, and the seed is the same, the random generator block will generate the same set of random numbers each time. So they are not really random numbers, they are what we call pseudo-random numbers, okay? Because they use deterministic algorithms that if you give them the same initial condition, which is called the seed, now we know the meaning of seed, they will generate the same random numbers every single time. So they are not really random, they are pseudo-random numbers. Now I want to explain that a little bit. What is seed? How is it that they generate pseudo-random numbers? And how we set the seed and everything. So these commands rand, rand_n, and rand_i, inside them, they have an option for the seed. So not only you can ask them to generate a matrix of 6 by 1, 6 by 2, 10 by 5, something random numbers, or a single random scalar random number, but you can also pass them the input option of seed, and then you pass them the seed number. Okay? Now, what is the seed number going to be? It is going to be a number from 0 all the way to something. What is that something? It depends on the deterministic algorithm. For instance, for this Twister algorithm, which is the default algorithm of MATLAB, this is basically this guy here. If I show you, we're going to go, right? So you can see that it is really, let me go down. So the maximum number that it generates is 2 to the 32 minus 1. So this is the maximum number you can use for the seed, okay, if you use the Twister algorithm. But the other algorithms, they are different, okay? So it could be any number in this range for the default algorithm in MATLAB, the Twister. So let's talk a little bit about it. So as I said, these commands, they have their own option to pass the seed to them. And if you use a different seed, they create a different set of random numbers. And if you go back to the same seed, you can get the same set of random numbers that you generated last time. And I'm going to show you in a MATLAB code in a minute. But let's talk a little bit behind the scene and see what's inside these commands and how it works. But other than these three commands that can get their own seed, there is a specific command that is just for setting the seed, and this is the RNG command in MATLAB, random generator. And this will set the seed for you. So when you use this command, not only you can pass the seed value, you can also, as a string, pass to it the type of the generator. And there are three generator algorithms in MATLAB. One of them is the Mersenne Twister algorithm, the default one. There is this Philox algorithm, and there is the 3-Fry algorithm. This is the top one is the default one. These two also are the two other, so there are three of them. Now, what's the difference between them? Let's talk about it a little bit in a second. So, first of all, as you can see, they are all pseudo-random numbers. Now, these two algorithms are called counter-based random number generators. What is counter-based? I don't want to get into depth of that because that opens another can of worms, so I don't want to make this video very long. But their essence of algorithm is a little bit different, but again, they are deterministic algorithms, and you can get the same result each time using them. Now, the period of the random numbers that they generate for the Twister algorithm is very, very large. For these two are the same, 2 to the 128. For this one is something like 2 to the 20,000 minus 1. So this can generate a huge sequence of numbers that don't repeat, okay, for the same seed. You can see that these numbers, none of these numbers is like any of their previous ones. It takes these many numbers to generate with it until you see one of the previous data back. Okay, so they look a lot more random than these guys do. And of course, they have states. This is the part that they are different. So these guys have states. These guys are stateless or based on counters. Again, I don't want to get into that, maybe in a separate video. Now, so if we want to generate long streams, of random numbers, that none of them is like any of the previous ones, the Twister algorithm is better than the other two. Now, if we want to use parallel computing and you have several cores or several hundred or thousands of cores, and you want these random numbers to be generated fast, then these two algorithms, the Philox and the 3-phi, are really meant for the parallel algorithm, because in here really each state is dependent on the previous one, so you cannot run it on parallel processors, but these two you can. Now, are they cryptographically secure, right? Can you break into them and find the next number and so on? The matter of fact is the first two are absolutely not. The last one is kind of inspired. It's not really safe, but it's better than the two other ones. And in terms of the speed of the algorithm itself, the Twister is fast for a sequential use, and this middle one is fast for parallel, as I said, and this last one is a little bit slower than Philox. So when it comes to being fast and basically parallel processing, I recommend the Philox. When it comes to large sequence of random numbers and you don't care too much about the speed, I think Twister is good. And if it comes to having a little bit more security in terms of not being able to break into it and guess it, probably the 3-phi is a little bit more secure than the two others. Okay, so this is when and when to use them. Now, as I said, using the command RNG, you can set the seed and you can choose the algorithm. Now, if we want to be able to regenerate a previous sequence of random numbers, all we need is to remember what seed we have used. Now, if you didn't set up the seed using this command, if you didn't specify that and just use the random number, so you use the rand and 1 and 6 and you generate some random numbers, but you did not provide the seed, so MATLAB used some seed for it. Okay, but what seed did MATLAB use? Because I forgot to give it. So MATLAB used one of its own. What was it? Can I get it and reproduce the number? The answer is yes. The way to do it is by just calling the RNG command and assign it to this variable s. That will give you the state of the random generator, and that inside of it, it has the seed. So as long as you say s equal RNG, that will give you the information that now if you pass it to the RNG command, you are setting what? You're setting the random generator seed to whatever it was in last time. So just by using this command, after you did some rand command or something, getting this, passing it to the RNG. Now, if you do another rand command, both of these will generate the same number. Okay? So, and if you want the RNG to go back and restores the default setting, you can use the command RNG default. Okay? Now, first, let me show you the MATLAB code, the simple MATLAB code that I wrote to demo this. And then I want to explain how this Twister algorithm, which is MATLAB default, is working. Let's look at the code. So here, I'm using a seed of 42 and the algorithm Twister, and I initialize my random generation with seed and with the algorithm. So here I'm setting it. Now I generate a sequence of 1 by 5, a vector, a matrix of 1 by 5 random numbers from a uniform distribution between 0 and 1. Okay, that is what the command RND does. I generate them and then I show them. Now, when I ran that, the numbers it generated were these 5 numbers, okay, between 0 and 1. Fine. Now what? Now I want to use the rand of 1 and 5 command, but I want to regenerate the exact same numbers. If I don't use the same seed and the same algorithm, when I run this command, I'm not going to be able to regenerate the same numbers. But if I do, yes, I can. So what do? This RNG, okay, that gives me the state of the RNG command, I save it to a variable RNG state. Here I call it here I call it S instead. So this is the same as S here. And then now I can basically reinitialize my RNG command with either seed and algorithm or with this RNG state. Now let me show you what this RNG state is actually, because you might not see that. So let me show you what this one does. You see? So it shows the algorithm, it shows the seed, and it shows the states. Okay, and I'll talk about this UN32 and so on. But you see that it has all the information. So can I pass this to the RNG command? When I got it, can I pass it to it? We'll find out. And then I generate a new sequence of 1 by 5, call it random number 2. Remember, the original ones are random number 1. And then I say, is equal random number 1 and 2. So I compare them 1 by 1. And then I use the assert command. Assert will generate an error if the condition of it is false. So if it's true, no worries, okay? It says reinitializing RNG produces identical result. But if this condition is false, these two sequences are not the same, even a small difference, then it says the error, which is the sequences do not match. And then, of course, it shows the second random set of random numbers. So let's go ahead. Now, you see here, it says the sequence do not match, right? You see, it says the sequence do not match. So what was the problem? Here, this state that I got, I passed it to RNG and apparently could not regenerate the same thing. Why? Because all it needs is the seed and the type. So, and this is a structure that also has states in it. So if I say, remember the command to do, if I want to go back to what we had, it was this, okay? Seed and algorithm, and seed is the RNG state dot type, and that one is dot seed. So if I say this one dot seed and this algorithm is this one dot type, would that do it? Because now I got it, I got those fills from the structure that I want, and I regenerated it. Let's see, there we go. You see, and these two are exactly equal. So you don't want to pass the entire variable of states to it, because not only it has this twist, the algorithm and the seed, it also has that state, which is not what this RNG command needs. So here I saved it, I got the fields I needed, and I regenerated the same thing, and I checked it with the assert command. Now, if you change the seed from, it was 42, now if you change it to another number, 123, look, the numbers are different. Clearly, you can see that it's different number. Or if you change the algorithm, here we change it from Twister to Philox, and you see I have different numbers. So changing any of those will change the sequence that you will get. Now let's go back and look at this Twister algorithm, Mersenne Twister algorithm, or MT, which is a pseudo-random number generator, or PRNG algorithm, which generates high quality sequence. Why high quality? Because the period of it is huge. Okay, how does this algorithm work? Let's take a look. So the first thing is it initializes the state vector by the seed. So seed is your initial number. Then what? Then the subsequent elements are generated using this formula. Si, the ith element in the state, is f times, this dot is like times, it's not a dot product, si minus 1 bitwise exclusive OR by this guy here, which is si shifted to the right, w minus 2 times, and w is a fixed number in this algorithm, 32, which is the size of a variable of type word, or 4 bytes, or 32 bits. So w minus 2, that is, this number is 30 in this algorithm, plus I, then modulus of 2 to the w. So the operations in this, there is a modulus, there is addition, there is shift bit to the right, there is exclusive OR, there is multiplication. So there are several things. And to show you how this really works, and this f is a constant number in this algorithm, the constant is this big number, right? So you can see that is about 1.8 billion is the number for f. So let's start with a seed of 1. So here we start with s not equal 1, the initial seed that we pass to this algorithm. In 32 bits, remember it was u int 32, I guess, correct? That's because each number here is shown with unsigned integer 32 bits. That's why. Okay, remember when we ran this command here, this one, look. Not that one, I'm sorry. It's this guy here. You see, u in 32, that's this reason here. So number 1 is, of course, stored like that, a bunch of zeros and a 1 at the end. W minus 2 is 30. First, we right shift S0 30 bits to the right. Okay, so if we do 1 bit, each one will move to the next one. That is 1 bit shift to the right. If you do 30, then each bit will be shifted 30 to the right. So this guy here, this is 31, 32. This 1 goes to 31. So this guy comes, sits right here at 31. That 0 sits here right at 32. And the rest of it that are not available, they're going to be just a bunch of zeros. So the number will be basically all zeros. So when you shift it 30 to the right, the number will just simply be 0. That's the result of this portion here. This portion, the result of it will simply be 0. Then what? Then you do a exclusive bitwise bit XOR with the previous I. So with the S0, you bitwise exclusive OR operation, the new result with that. What does that mean? Means these two numbers. Means do exclusive bit between this one and this one. So between each 2 bits, you do exclusive OR. 32 bit with 32, 31 with 31, all the way to second with second and first with first. And you know, XOR of 0 and 0 is 0. So 0 XOR 0 is 0. But 0 XOR 1 is 1. Correct? You all hopefully know the exclusive OR. So all of the zeros will be 0. That last one will be 1. So your final number still going to be what? It's still going to be 1. So the result of now this portion will be 1 Then you multiply it by that 1.8 billion. Finally, you add this I of 1 here, because the seed is S naught. So S1, the next number, you have to add I of 1 here. So you add a 1 to this result. So you get this guy. 2 to the 32 is this number here, about 4.2 billion. So now you do 1.8 billion modulus 4.2 billion, which brings back the 1.8 billion. Seems like this number is repeated twice. So this is going to be the result. That's it. That is S1. Now you use S1 here, that 1.8 billion, you use that here and repeat the operation to get S2, and that for you I have shown down here. So if you write this number as 32-bit, this is going to be it, and then you have to shift it 30 bits to the right. And if you do that, only these two will remain. The rest of it will be a bunch of zeros, so that's why you see this 1, 1, which is number 3. Now this one will be XORed with that one. All of the zeros will be 0. And then the zeros with zeros are 0. Zeros with 1 are 1. 1 and 1 is 0. So XOR bit is going to be this, which the decimal value of it is, of course, this 1.8 billion. Multiplied by another 1.8 billion, you get this very huge number. For I of 2, you add 2 to it, and take modulus of 2 to the 32, you get this number here, which is about 1.9 billion. So S2 is 1.9 billion. Then plug S2 into that formula, go back, repeat, right? So this is the binary representation of it. 30 bits shifted to the right. Again, these two are the only thing that will survive. Then you do XOR bitwise between them. You get this. The value for it is again something close to 1.9 billion multiplied by 1.8. You get this number, add a 3 to it, take modulus of 2 to the 32, and you get 1.2 billion. Okay, so these are 4 of the numbers. You started with 1. The next number was 1.8 billion. The next number was 1.9 billion. The next one was 1.2 billion. Now you might say, remember you told me that the command RND generates number in the range 0 to 1. These guys are all in billions. How would you go from those numbers to 0 to 1? Here you need to do a linear transformation. Remember, the biggest number this algorithm can generate is 2 to the 32 minus 1. So it generates numbers from 0 to this number. So these numbers, S0, S0, S1, all these that you get, you have to divide them. If you call them X, you have to divide them by 2 to the 32 minus 1, the maximum thing. And the result of that, this Y, is going to be something that you see in the RAND command. This is definitely going to be between 0 and 1. So if we do that, the first number corresponding to the seed that we get is a very, very small number, like 10 to the negative 10. The next number is 0.42. The next number is 44. And the next one is 0.28. Okay? So this is how it generates 4 random numbers. If we do that one more time, then we get 5 random numbers. And this was with the seed of 1. Now, if we do that with the seed of 42 or 123 or something, we are going to get these guys. So hopefully it is clear now how MATLAB is generating random numbers, the fact that these are pseudo-random numbers, the fact that there is a seed, there is an algorithm, and you can reproduce them, and when to use each one of these generating algorithms based on the largeness or quality of random numbers, based on whether you want it to be done fast with parallel processing or you want it to be a little bit maybe secured to cryptography. Thank you so much for your attention, and I'm going to see you in the next video.